So unfortunately, Mike Wolfberger was not able to come to this meeting, so I'm going to be giving his invited talk on his behalf. Laser. So this is a review or tutorial style talk reviewing the current state of the art of global simulation studies of the effect of ionospheric outflow on the magnetosphere-ionosphere system dynamics. And as a review study, it summarizes the work of many more people than just Mike Wolfberger. So there's lots of people that need to be thanked. And when we get to the discussion section of this, those of you who are in the audience, please feel free to chime in. So as an outline, I'm going to talk about the general motivation for including ion outflow in global MHD simulations, give some background on global models, and then talk about the impacts of the magnetosphere, starting with results from simple numerical experiments, and then moving on to causally regulated outflow models, and I'll finish with the discussion of polar wind modeling. So we've known that O+ can be a part of the magnetosphere ever since the 70s, and recent observations have shown that it can actually become a main component of the plasma sheet during strong magnetic storms. Shea and Swizdak have suggested that it influences reconnection rates based on multi-fluid MHD simulations. Most of the early work in creating magnetospheric general circulation models, or GCMs, has concentrated on the electrodynamic coupling between the magnetosphere and the ionosphere. But now that we have multi-fluid versions of these GCMs, it's now finally possible to address the effect of ionospheric H+ and O+ on magnetospheric dynamics. So just a review of electrodynamic coupling. A GCM will consist of three main components: an MHD simulation of the magnetosphere, a magnetosphere-ionosphere coupling module, and an IT model. And this coupling module, its core function is to solve an elliptic equation for the ionospheric potential given the field-aligned currents coming in. And it also has to deal with precipitation inputs to come up with these ionospheric conductivities somehow. And then once you've solved this, you map this potential back up to your inner boundary of your magnetosphere model to set the inner boundary conditions on the perpendicular flows. Now, doing mass coupling in a GCM is difficult because most of them have a giant gap. So in the case of the CMIT model, which is the marriage between the LFM magnetosphere model and the TiGCM ionosphere thermosphere model, the top of the TiGCM, it's a pressure level, but it typically varies between 500 and 800 kilometers. Whereas the inner boundary of the LFM is at 2 RE geocentric, so 6,300 altitude. So there's this giant gap that nothing can flow through. But of course, there is mass flowing through this region. The inner boundary conditions on the magnetosphere are normally hard wall conditions in the LFM. So there's no mass passed through the inner boundary, and I should mention that the LFM works differently from Betz or Russ, such that it really is a hard wall. There's no passive outflow coming out. The V parallel is simply reflected, and the V perp comes from the electrodynamic coupling. To put an outflow in, which is an inflow into the magnetosphere region, you need to specify the location of that outflow, and the location matters quite a bit, and I'll come back to that point. Knowing the mass flux is useful, but that's not enough. You need to specify all of the MHD variables, so parallel velocity, temperature, and so forth. So the multi-fluid version of the LFM model is the main differences between it and the standard LFM model is that it solves mass, parallel and perpendicular momentum, and energy conservation equations for each plasma species individually. And these equations are such that the plasma species move together perpendicular to the field, and they move independently parallel to the field. And then in addition to all the normal requirements for setting it up an MHD model, you need some specification of the plasma outflow at the inner boundary. So I'm going to talk about the impacts on the magnetosphere on the magnetotail, focusing on basically three different classes of studies. I'm going to start with some simple numerical experiments where outflow was specified to come from fixed regions. And then I'm going to move on to experiments where empirical relationships derived from fast data were used to come up with causal regulation conditions for the outflow flux and its location. And then finally, I'm going to talk some about the polar wind modeling group, the polar wind outflow model, which has been used by the Michigan group. So here is a simple example from Wolfberger et al. 2010, where cusp outflow was simply specified to be coming out of these yellow cells here on the day side, with a fixed flux and a fixed velocity, and so forth. And in the movie I'm going to show you, The left panel is a baseline run of the single fluid LFM, and the other panel is the multi-fluid run. This panel is showing the log of the H plus density. This panel is showing the log of the O plus density. And in both, the red lines are magnetic field traces. And what you're going to see is the O plus coming up out of the cusp and going back into the tail. And then here, a second substorm kicks off in the multi-fluid simulation, which was not observed in the baseline single fluid simulation. And this second substorm is not observed every time that they add outflow. It actually really depends on the properties of the outflow that they pump in. So what really matters is whether or not that outflow lands in the correct spot back in the tail. If the outflow comes out too fast, it'll just shoot down the tail, and it won't actually cause that second substorm to occur. So watching it again, there's a substorm that kicks off in both simulations, but then right in that region where that outflow landed, that's where you get that second substorm kicking off. And studies by Yu and Ridley with the space weather modeling framework with fixed cusp outflow have found some similar conclusions, that the dynamics heavily depend on the properties of the outflow that come out, because that determines where it actually ends up back in the tail. So moving on to causally regulated studies with the MFLFM. Here's Bin Zhang's diagram of how their causally regulated algorithm works. You start in the LFM and go to a surface of 3RE inside there. You pick out the electric and magnetic fields there, and then you bandpass filter them between 5 and 180 seconds to pick out the so-called alphanic component. Take the cross product of those two will give you the Poynting flux, and then you map that Poynting flux down to fast altitudes, to 4,000 kilometers, and then use an empirical relationship derived from fast data to come up with an O plus outflow flux given that Poynting flux, and then map it back up to the inner boundary. And then when you apply that, just having that flux is not enough. You also need to assume a parallel velocity and a temperature. So the assumed parallel velocity, the assumed temperature, and the coefficient out here in this empirical relation are all kind of tunable parameters. And this causally regulated outflow mechanism has been used to great success to model sawtooth oscillations. So here are results reproduced from the Brambles et al. 2011 Science article. The black line, this is magnetic inclination angle. And the black line here is a baseline run with no outflow. And you can see there's not really any oscillations. And then the other two lines are two different runs with outflow, where the red line has much higher fluences than the blue line. And you can see in both of these you get oscillations, and the period of these oscillations increases with higher fluence. A more careful examination of these sawtooth events by Wallet et al. 2013 has shown that they actually occur from a feedback loop. They would not appear if this outflow was not being causally regulated. So the one substorm kicks off, it injects alphanic Poynting flux down into the auroral ionosphere. That creates more outflow, which then goes out, lands somewhere out in the tail, and then kicks off another substorm. So the group has moved on to doing, those were idealized simulations. They've now moved on to doing some event simulations, and these are summarized in Brambles et al. 2013. This is for a CME event, April 18th, 2002. The blue lines are a baseline run with no outflow, and then the red lines are again with this alphanic Poynting flux regulated outflow. And you can see sawtooth oscillations appearing in the case with the causally regulated outflow, whereas they don't without it. Now in this CME event, the solar wind conditions, it's fairly constant strong driving. If you compare this to a stream interaction region driven event where the solar wind driving is much more chaotic, the difference between the baseline run and the run with outflow is less pronounced. Both of them look like they have sawtooth oscillations. So in this case, it's not clear that the outflow is really necessary to be producing these sawtooth oscillations. So those are all just using empirical relationships. The Michigan group has really done a lot of work with actually incorporating polar wind models, physics-based polar wind. So the polar wind outflow model, we've heard it mentioned a couple times now. It's summarized in Glosser et al. 2009. It's a field-aligned, multi-fluid, multi-field line model. The single field line version is based on the classical polar wind model of Gombosi and Nagy 1989, and it's a Lagrangian model. So you start with a bunch of flux tubes, they convect around, and periodically you need to redistribute them because they tend to bunch up. So here's just a basic example incorporating the Plum with the Batsa-Russ. Here are O+ fluxes and H+ fluxes coming out of it. The color scales are different on these two, and you can see the O+ is both going up in some regions and down in some other regions. The H+ is basically going up everywhere. This is a run for a May 1998 event. This dashed line here is a baseline run without outflow. These are actual measurements. And then this curve is the run including the Plum outflow. And you can see adding that Plum outflow dramatically reduces the DST and causes it to actually overshoot the measurements for this case. So the Space Weather Modeling Framework group and the MFLFM group are using radically different approaches to specify their outflow. One is using physics-based polar wind, the other is using purely empirical. And yet the two groups have found some common results between their simulations. And one of them has to do with the shape of the magnetosphere. So here's an MFLFM result from Brambles et al. 2010, which was using empirical model regulated by DC Poynting flux in this case. This is a case without outflow, and this is a case with outflow. And you can see the standoff distance has increased. The magnetopause has moved out further by about 20%. And the magnetosphere has also become blunter in the simulation without outflow. And this change in the shape of the magnetopause at least partially explains an observed change in the cross-polar cap potential observed in the case with outflow. Here are some Batsa-Russ results. The green line is a baseline result, and the blue line is including the Plum. And you can see again, including the Plum outflow causes an expansion of the increase of the standoff distance and a blunting of the magnetopause. Now the red line in this is a simulation with the RCM included, but without outflow. And so you can see the inclusion of outflow is comparable to the inclusion of the RCM, at least in this case, in terms of the amount that it expands the magnetosphere. I mentioned a reduction in the cross-polar cap potential. This was actually first reported back in 2002 by Wingley et al. So the Wingley outflow method is basically a version of the passive outflow method that Dan Welling was talking about. What he does is he puts some density in his inner ghost cells, and then the pressure gradients and centrifugal forces just numerically pull that out. And a tunable parameter for it is the fraction of O+ to H+ in those ghost cells. So as you tune up that fraction in the ghost cells, you end up populating the model with more O+. And the different curves here represent increasing O+ ratio. And as you increase the O+ that in that inner boundary, you decrease the cross-polar cap potential, and for this particular event simulated, you actually bring that model down into closer agreement with the AMI assimilative results. So the different groups have all reported a reduction in the cross-polar cap potential, but there's still a debate as to why this is going on. I mentioned changes in the shape of the magnetopause, but that's not agreed to be the entire story. Wingley speculated that mass loading was actually the main reason for this reduction. So simulations have shown that the inclusion of outflow changes the MI coupling parameters and how the solar wind interacts with the MI system. In general, outflow causes the magnetotail to get wider and longer with greater fluence, and the cross-polar cap potential is generally reduced at least partially by changes in the shape of the magnetopause. Idealized studies show that ionospheric outflow can lead to multiple substorms and/or sawtooth events. Sawtooth events during steady solar simulations are the result of a feedback loop with outflow upsetting the balance between the day side and the night side reconnection rates. Sawtooth events can recur in response to different solar wind drivers. During steady CME-type strong driving conditions, outflow seems to be required, at least in these simulations, to get the sawtooth events. But in terms of much more chaotic SIR-type events, that's not necessarily true. Most of what I've talked about today is summarized at great more length in a review paper which was recently accepted to the Magnetosphere Chapman Conference proceedings. This review paper, it goes through the fundamental set of equations used by, oh, come on. goes through the set of equations used by the Wingley group. Yeah, there we go. So all the groups considered, the Wingley group, the Space Weather Modeling Framework, and the MFLFM, basically start from the same set of multi-fluid ideal MHD equations. The ions move independently along the field lines, but they move together in the perpendicular directions. The major differences between the three different groups are in how they apply the outflow. The Wingley group has only used this so-called passive outflow method. The Space Weather Modeling Framework, they can use this passive outflow method, but most of the stuff they've done has been with an actual physics-based polar wind model. The MFLFM cannot do this passive outflow method because its inner boundary conditions are fundamentally different, and the studies that have been done with it have either been with a specified location or with empirical causally regulated algorithms. Despite the profound differences in the techniques used, they've observed some common results. All the groups have reported seeing a reduction in the cross-polar cap potential, although there's considerable debate as to why this is being observed. And all have observed changes in magnetosphere dynamics. The O+ landing location back in the tail impacts whether or not you're going to see multiple substorm dynamics. The MFLFM group has reported a role for O+ in Sawtooth events, and both the Space Weather Modeling Framework and MFLFM groups have reported increases in DST with O+ outflow. Now, this review paper summarizes basically the current state of the art of what's been done, but there's clearly tons of room for future work to be done beyond this. And in my opinion, at least, there's a lot of things that can be done between what's been tried so far and the vision for the future that we heard from Bob Junk this morning of a kinetic model of everything. And so tonight, I'm actually going to be talking about polar wind modeling, including phenomenological treatments of wave-particle interactions. So I have a polar wind model that's somewhat similar to Plum, where I've added an extra fluid representing energized O+. And I have some ad hoc source terms that actually do wave-particle heating that I've applied in a region on the day side. And this energized O+ outflow that I get as a result doesn't stay confined to my heating region, but the convection actually pulls it out of the heating region and spreads it all over the polar cap. So these ions, energized ions, they don't just go up the field lines where I've applied the transverse heating, they actually get dragged back down along the polar cap. So please come to my talk this evening to hear more about this. Thank you.
Thank you very much. It was very interesting, and we have time for questions. Oscar?
Roger, if I could just add to one of the comments that you made. It is true that all of the published work in MFLFM, using MFLFM, could not treat a passive ionospheric boundary, but that has since changed, and we are in fact now doing a lot of different things at that boundary to try different ways of getting outflow or mass exchange through the boundary.
I think back in the old days, a decade ago or so, we were talking about having models like this, or suggesting that they would be useful. A big criticism was leveled against the whole idea in that we didn't have a really good physical model of the outflow that could be plugged into the models. And I think that's still kind of outstanding, and mostly for lack of observational details about how this wave-particle interaction goes on. And it just seems like I'm a little disappointed in getting too sort of fixated on the passive boundary condition. I think that's more of a desperate deed done to get something working.
I agree with you that there are huge challenges based on, I mean, there's a lot more work that needs to be done. So a lot of what I've talked about have just been simple numerical experiments to see if we pump in outflow here, does the code work? Does it run? What happens?
I'd just like to comment that I dislike this separation of the passive outflow and a physics-based outflow, because there's a lot of physics in the passive outflow. And as Alex was pointing out to us, that the in private conversations, that when you apply a density there, there's a temperature associated with it, and half of that Maxwellian, even if it is not, it has no radial velocity, is still upflowing. And so there's material upflowing even with a zero bulk velocity, and the physics is centrifugal or some other force that's acting on these particles as soon as they get into the MHD simulation domain. So there's a lot of physics in all the codes as the material is lifting out.
So my response to that is, when these passive outflow boundary conditions are applied, conservation of mass is violated. So when you use a physics-based polar wind model, everything that goes into the magnetosphere simulation, you've taken out of the polar wind. And so ions that get created down in the ionosphere get transferred up. If you just hold your ghost cells in the inner boundary at a fixed density, when you pull stuff out, the density in those ghost cells doesn't change, it's just held fixed. So there's essentially mass being created. Yeah. Well, my point is the source term to the magnetosphere domain should be a loss term to an ionosphere domain, and ultimately the amount that can come into the magnetosphere is limited by the amount that's being produced in the ionosphere. There's a cap to how big that could ever possibly be.
I'll skip that point. Two things. One, I want to caution against, while I like to say de facto, and the reason I like that is because while the boundary itself is passive in terms of the mass density about it, the source, after a few cells into the MHD computational domain, is no longer passive. It is a function of local pressure gradients and J cross B forces, so be careful there. And so that the passive term can get quite confusing when used sloppily. The other thing, changing subjects a little bit here, is going into this idea of the reductions in cross-polar cap potential. I'd like to make the whole situation much more confusing. Recently, Mike Lamone and I have found that if we change the inner boundary density in our single fluid MHD code 3 orders of magnitude, the fluence changes with that, not just about linearly. I have to look that up, make sure I'm right. I could be wrong. I have to think about that. It changes quite. It's in the paper. The cross-polar cap potential changes maybe 10 kilovolts. When you turn on the polar wind outflow model in the same simulation setup, instead of just keeping a constant radial and inner boundary density, the cross-polar cap potential drops 50 kilovolts. Further, to make this whole picture much more murky, Wingley saw all these effects using this kind of de facto constant inner boundary setup, but his was a multi-fluid approach. So, more to chew on.
I want to go back to the passive boundary. So what comes out of the ionosphere is a source of the upwelling or the pushing from below and the sucking by wave particle interactions and on that. And when you use a passive boundary, you're basically ignoring variations in magnetic local time of upwelling and wave particle interactions.
I agree.
And you're assuming that the ionosphere is doing exactly what the magnetosphere tells it. But those of us that have played with the magnetosphere knows that it's like a wife. She has her own mind.
Yes, I'd like to follow up on Dan's comments. And it is an interesting problem, and it to be resolved as to exactly how the outflow's regulating the cross-polar cap potential. But there's an important thing to keep in mind. The solar wind is coming regardless of how much outflow is coming out of the ionosphere. The solar wind continues to come up against the magnetopause. And you've got two competing processes at the magnetopause. Either you can reconnect that magnetic flux at the magnetopause, or you can convect it around the magnetopause. But one way or the other, those are the only two ways to get rid of that flux that the solar wind's bringing in. And so the explanation for how the outflow affects a cross-polar potential can't just be an internal mechanism. It can't just be that the magnetosphere is inertially loaded and the convection is slower, because that doesn't say anything about the solar wind. The solar wind is still bringing this flux in. So, I mean, the one process has to do with changing the shape or the dynamics in the magnetosheath and changing the shape of the boundary to change the relative proportion of reconnective versus convective transport of flux. But I think it's fair to say we still have a lot of work to do before we can really tease out the exact mechanism.